In this video, I will talk about the concept of mutual inductance, and the symbol we use for that concept is the uppercase M. I have here two loops. I have loop 1, I have loop 2, and in this part of my monitor, I'm showing the work that we do to go from the current in loop 1 to the induced EMF in loop 2. So from the current, from I1, I can use Biot-Savart's law to calculate the magnetic field that the current here creates at the location of loop 2. And then once I have the magnetic field here, I can use it in conjunction with the definition of the magnetic flux to find the magnetic flux at loop 2. And once I have the magnetic flux there, I can use Faraday's law to find the induced EMF in loop 2. Now, we know, of course, that Biot-Savart's law is a lot of work, and there is nothing wrong with that. Sometimes, though, we do want to make our calculations more efficient. And not only we have to use Biot-Savart's law, but we also have to use the definition of the flux. The concept of mutual inductance allows us, so this is a lot of work. Not just there, but also going there. So we do a lot of work to go from I1 to the induced EMF on the other loop. And the concept of inductance is the following. If I take I1 and I multiply it with the mutual inductance between 1 and 2, then this can give me the magnetic flux that goes through loop 2. Okay, so if you see here, instead of using Biot-Savart's law and the definition of the magnetic flux to find this, the concept of the mutual inductance allows us to bypass all of that and go directly here. If we have this number, okay, this is a number. Now, but the thing is, once you find mutual inductance for your system, like meaning if you keep coil 1 and coil 2 or solenoid 1 and whatever else you have at 2, if you keep those two instruments the same, then once you find the mutual inductance for your system, that's it. You found it, you have it, you can use it as many times as you want. Now, I want to mention one thing. The mutual inductance, whether you're interested in finding the EMF, induced EMF in loop 2, or the induced EMF in loop 1 from the current from I2, it's the same. It's the same number. Okay. So once you find it for your system, actually it's the same whether you go from 1 to 2 or from 2 to 1. Now, so as I said, the concept of the mutual inductance allows us to make our calculations more efficient. It does take a lot of work, though. Okay, I'm not saying that this can be done. Fast. If nobody gives you the mutual inductance, it will take a lot of work to find it. Okay, I'm not saying that this is simple. But if you buy an instrument like the 2 coils, for example, if you buy them, then it is very possible that the manufacturer of those two of that instrument, they have made the measurements and they have already found what is the mutual inductance for that system. And if they give you this number, then you can bypass this a lot of work. All right, so once you have now the magnetic flux, assuming that you do it in an efficient way, using mutual inductance, then you can use it in Faraday's law. Now, this is how you're going to do it. So the induced EMF in loop 2 is minus the rate of change of the magnetic flux that goes through loop 2. But this is equal to I1 times the mutual inductance between 1 and 2. I'm not including any arrow this time because really, whether it is from 1 to 2 or from 2 to 1, it's the same thing, okay? And then I know that I have to use the product rule where I have the change in I1 delta T, the mutual inductance between 1 and 2, and then the change in the mutual inductance between 1 and 2 over delta T. But this is a number, and this number is a constant, so this is 0, and this means that Faraday's law, using the concept of the mutual inductance, takes this form. So this way, using the concept of the mutual inductance, you have a direct relationship between I1 and the induced EMF. Okay, so the concept of the mutual inductance allows you to bypass all of this work and connect the induced EMF in loop 2 with a change in the current in loop 1. Very important, and it is very useful to know this relationship and to see it, actually, to see it in an expression. It does help us understand that it is the change in the current 1 that is related to the induced EMF in loop 2. In any case, the concept of the mutual inductance allows us to make all of this in a more efficient way.